Okay, so I want to talk to you about the standard normal distribution, what it is and how to use it and how it's used. Here's your first definition of the standard normal distribution right here. Standard normal distribution is the graph of the entire collection of z-scores for any normally distributed variable x that has a mean mu and standard deviation sigma. So if you have a normally distributed variable x and it's centered at, say, mu equals 10, well, we know that there's an infinite number of z-scores appearing along this axis, along this x-axis. That infinite number of z-scores, if you could find, I'm sorry, the infinite number of x values over here, if you could find the z-scores for every one of those values of x, that collection would be called the standard normal distribution. And it doesn't matter what the value, what the variable x represents, nor does it matter what the mean and standard deviation of the normally distributed variable x is. Every normal variable x will have the same set of z-scores. So it doesn't matter what the normally distributed variable x represents, nor does it matter what the values of specific values of mu and sigma are. Every normal variable x will have the same set of z-scores, and this is called the standard normal distribution. So I want to talk to you about the properties of the standard normal distribution and what the z-table is and how we use it. And here's your second definition right here of the standard normal distribution. The standard normal distribution is the normal distribution that has a mean mu equal to 0 and a standard deviation sigma equal to 1. And so if the mean is 0, that means that the standard normal distribution is centered at the origin, or it's centered at 0. And here's your properties of the standard normal distribution. We know that it's a collection of z-scores for any normally distributed random variable x. We know that it's centered at the origin because the mean is 0 and the standard deviation is 1. Furthermore, the cumulative area, so we need to talk about what cumulative area means. And if you take a look at this graph right here, I've got a graph of a normally distributed random variable x, and I've located 5 along the x-axis. The area to the left of 5, the area under the normal curve left of 5, is called the cumulative area of x equals 5. So to understand how this standard normal distribution properties work, and also how to use the z-table, you need to know about the definition of what a cumulative area is, okay? And so here's that definition. The phrase cumulative area is used to indicate an area under a curve that is left of a specific number located on the horizontal axis. So that's So here's a picture of that once again. Cumulative area is just used to indicate an area that is to the left of a specific value along the x-axis of the horizontal axis. Okay, so let's go back down here and look at the properties of the standard normal distribution of z-scores. And they're talking about cumulative area. So the cumulative area is almost 0 for z-scores close to negative 3.49. So, and the cumulative area increases as z-scores increase. So an illustration of that, let me see if I've got one here. Here's your standard normal distribution. And right now, My cursor is pointing to z equals -4, -4. And the area to the left of that value, or the cumulative area, is, look at that, about 0. It's pretty close to 0. And look what happens to the cumulative area number, this number here. As I increase the value of z, you can see that the cumulative area associated with that z value is increasing as well. Once you get up to z equals 0, the area is exactly 50% or 0.5. And moreover, z equals 0 always corresponds to the mean of x. And finally, the last property, the cumulative area is close to 100% for z-scores, close to 3.49 standard deviations. And you can see that if we continue to move this z value along the z-axis, you can see that the cumulative area increases, and we get to about 3.49, and you can see almost all of the area, all of the cumulative area is about 100%. So that's properties of the standard normal distribution. And another one that I mentioned, it might be easier to see if you take a look at the this right here. Okay, so we know that the z-score of the mean of x, the mean of x, is actually 0. Since the z-score formula tells us so. So add x equals mu. The z-score is mu minus mu over sigma, okay? And the numerator becomes 0 over sigma, and of course that is 0. So it's just a property of the z-score formula. And then that also tells us that the center of the normal distribution is going to be at the origin, or at 0. Okay, so now I want to talk to you about the z-table and what it is. The z-table is it's a sheet, a 2-page sheet that you can find in the back of every one of these textbooks for the class. I'll show you how to find a copy of that. Just go over here to the sitemap button and click on probability tables. And there's a whole bunch of information here, but this table of contents over here, I'm just going to scroll down to where it says z-table and click on that. And the z-table, it's there on the web page, but also if you want to download a PDF of that, the link should be right here. Okay, so back to the z-table. I want to talk about what that is and how we use it. Here we go. For the book I used to teach out of, the z-table was in Appendix B, Table 7. In this book, it might be different. But what you need to know about the z-table is the following. It's designed only for the standard normal distribution, which has a mean of 0 and a standard deviation of 1. The z-table is on 2 pages with 1 page for negative z-scores. And the other page will be corresponding to positive z-scores. There's always 2 pieces of information on the z-table: z-scores and probabilities. The leftmost column, highlighted here, and the top row of the table are associated with z-scores or z-values. Each value in the table body of the, each number in the table body is a cumulative area. Whoops. It's a cumulative area from the left up to a specific boundary above a specific z-score. So that was a little too much verbiage, but the numbers in these table values, they just give you this right over here, this cumulative area for corresponding to a particular z-score. So let's show you how that works. And of course, these areas are mathematically equivalent to probabilities. If you go up, the part of the z-score, which represents the hundredths, is found upon the top row. And that's something to keep in mind here. Let's take a look at this example to help you understand how it's used and how it's set up. So here we go. It's the Precision Scientific Instrument Company manufactures thermometers that are supposed to give readings of 0 degrees Celsius at the freezing point of water. Tests on a large sample of these instruments reveal that at the freezing point of water, some thermometers give readings below 0 and denoted by negative numbers, and some readings above 0, denoted by positive numbers. Whoops, here comes the question now. Assume that the average reading is 0, so assume that the mean is 0 degrees, and that the standard deviation of the readings is 1 degree. So the random variable x here is representing the temperature of a randomly selected thermometer, what reading it gives at the freezing point of water. Okay, so if we assume the readings are normally distributed, the question is this: if one thermometer is randomly selected, find the probability that at the freezing point of water, the reading on the thermometer is less than negative 1.51 degrees Celsius. Okay, so to use the z-table, basically before we do, let's see here, we need to convert the x value to a z-score. Okay, so we know that the distribution is normal. X is going to be the continuous random variable representing the temperature of a randomly selected thermometer. And so what we need to find is this probability right here. The probability that x is less than a negative 1.51. So the way this is done is we need to now find the z-score of x equals negative 1.51 with the z-score formula. So we do a plug-in, and we get negative 1.51. So this is a special case where the values of x here will also be equal to the values of z, but that doesn't always happen. Nevertheless, the probability we're trying to find is equal to this area right here underneath the curve, the cumulative area to the left of, since it's a less than, we're looking for the area to the left of negative 1.51. So how that's done with the z-table is the following. So we locate the row. So what we're going to do is, let me also show you this. We're going to take that z-score and we're going to split it up into two pieces. Okay, we're going to split this up into negative 1.5 plus negative 0.01. So this is a true statement. And the reason we're going to split that up is now, if you want to look up the cumulative area associated with negative 1.51, then you're going to need this part of the z-score. You're going to look that up in the first column, and the hundredths part of the z-score, you're going to look that up in the first row of the z-score table. So I'm looking for this number in the first column. I'm looking for this number in the first row. Check to see how that works. So here I am. Can you see I'm down here? Z equals negative 1.5. There it is. And so I've circled the row that corresponds to that. And now the next thing to do is look for the hundredths part of the z-score, 0.01. And what happens is the intersection of this row and column gives us this probability right here, 0.0655. So the answer to the question is about 6.55%. It's just equal to the cumulative area to the left of z equals negative 1.5. If you wanted to, you could use the calculator to find that same probability. We're going to press second bars, and we want to access normal CDF command. And here we'll use our lower will be negative 10 to the 9, upper will be negative 1.51. Make sure mu and sigma are both 0. And when we paste that in and hit enter, we can see we're going to get that, that probability. So if you have to answer a question like this, I recommend you use normal CDF on the calculator, but at the same time, you can use the Z table as the answer should be the same. What else have I got on here? So when you notice, take a look at your Z table, okay, the negative z-score side. Notice all of these, notice the sequence of numbers in this first column right here. It starts at negative 3.5 and lower, and you see they start to increase. So what happens is, as the values of Z increase, so do the probabilities or the cumulative areas until finally on this last row, the value of Z increases to 0. And that's where you're going to get a cumulative area of, you can see, as you can see, 50%. And if you go and you look at the positive z-score part of the table, you can tell it starts in this first column. Z values start at 0 and they start to increase. And you can make a similar statement here that, hey, as we increase the value of Z, the cumulative area or the area left of that value also increases. And okay, so here's a problem for us to try. We want to find what is the probability that Z is less than 2.37. The way to do this is split the z-score up into 2 parts, okay? Right, Z equals 2.37. When we split that up into 2 parts, it's 2.3 plus 0.07. And so therefore, we look for 2.3 in the first column. There it is. And then the 0.07, we're looking for that in the first row up here. And now the row column intersection will give you a single probability right here. And so then this probability is about 99.11% or 9.9911, the emergency probability, right? Okay, so that's how you use the z-score table. We got any other examples here using that? Okay, so how about, and going back to this problem here, the area left of 2.37, of course you could just use your normal CDF command if you wanted to find that area. In this case, we just need to change our upper boundary to 2.37. And we're going to keep the values of mu and sigma to be 0. And we get the same probability. Okay, so the Z table is useful to find probabilities or cumulative areas. Okay, here's one more example of using the Z table. Find the area between Z equals negative 1.51 and 2.37. Okay, so we're looking for this area, the area between these two numbers. And of course, if you want to do the problem the easy way, you're just going to use your normal CDF command, okay? And in this case, your lower number is going to be negative 1.51, and your upper will be 2.37. going to keep the values of mu and sigma at 0 and 1 respectively. And then bam, we're going to get the answer. It's about 92.55%. Okay, so the way to get, and unfortunately, the way to get that with the z-table is a little bit complicated, okay? What they have to do is you have to, because the z-table only gives you cumulative areas or areas to the left of a value, you have to actually split this probability up into the difference of these two probabilities, okay? So think about what this difference means right here. We're gonna look up in the z-table the cumulative area, or the area to the left of 2.37. So that includes this green area plus the white area over here. And then we're going to subtract off the probability z is less than negative 1.51. So basically, when we get this number, this first probability on the z table, that's going to give us the areas. It sums up the green area and the white area here. And since that's too much area, we've got to subtract off the white part to get. So to do the probability that z is between two numbers, if you're going to use the z table, you've actually got to look up. You've got to split it up in this way and do a subtraction, and you've got to look up two values of z in your table and subtract them. And if you want to find the probability that z is greater than 2.37, then when you look 2.37 up in the z table, of course we know we get 0.9911, but we don't want to report that as our answer, right? The area we're trying to find is just to the right here. There's no way that could be 99%. So if you're going to use the z table to do this one, then you have to use the complement rule. You have to take the total area underneath the curve, which is 1, and then you subtract the area to the left of z equals 2.37 to get the area. And of course, you can just use normal CDF to find that same area. I'm pressing second bar is 2, and I'm calling on normal CDF here. This time my lower boundary would be 2.37. And I would want my upper boundary to be 10, let's just go 10 to the minus 9 power. And let's see here. Well, now what happened here? Let me see, did I do? Yeah, what did I do? So it seems like I made a mistake here. Let's find out where it is. 2.37 upper is going to be 10 to the minus, oops, not 10 to the minus 9. It needs to be 10 to the 9. Okay, so that was the mistake I made. Because see, 10 to the minus 9 is almost 0. And my upper boundary needs to be an approximation of infinity. Okay, so that was the mistake I made. And you can see, look, we're getting the same answer as what we got using the z-table. So the z-table, it's used to find areas for z-scores, but also for normally distributed random variables x. And let me show you a problem that we've done before. Boy. And I'm going to use the z-table to find it. Let's see here. I want to do that. No, not that yet. Yeah, here we go. Okay, so this looks like it is off. Is this a lab? I believe this was. Let's see here. No, not that one. Okay, so it looks like it's lab 11. And what I'm going to go back and work with the z-table here in a little bit. Before I do that, let's take a look at these first 3 problems right here. And I'm going to show you how to do both the problem both ways with the Z table and the calculator. You should already know how to do this with the calculator. So take a look at the wording up here. In exercises 1 through 3, the random variable x is normally distributed. Mean mu is 174 and standard deviation is 20. So in question 1, they want us to find the probability that x is between 172 and 192. So first thing I would do is just draw a picture of the normally distributed variable x, and the mean is 174. So we know that the normal curve is centered at 174, and we also know that the standard deviation is 20. Okay, good. So now going back to question 1, I'm just going to locate the endpoints here, 172 and 192. So this number right here is probably 172 and 192. Let's see here. Is, I don't know, about right here. And this question just simplifies to having us just find the area between those two values, 172 and 192. And so I'm going to show you the easy way, and I hope that motivates you to do a problem like this way instead of using the Z table. But yeah, I'm pressing second bars 2. Bring up the normal CDF command here. This time my lower boundary is going to be 172. My upper boundary will be 192. And I've got to change these values of mu and sigma to 174 and 20. So I've got to change them away from 0 and 1. Paste that in, and bam, I am done. So question 1, we finished that. And we found out that the answer is about 0.3558. And what I've done there is I've rounded the probability off the calculator to the 10,000ths, or to 4 decimal places. And the reason I've done that is if you take a look at your Z table, all of these probabilities are rounded to 4 decimal places, or to the 10,000ths. Okay, so that is what's commonly done. That's how you do that problem. If you had to do that problem using the Z table, it wouldn't be so pretty. Yeah, so step 1, I need to find the Z score. Of 172 and 192. And I'm using the Z-score formula to do that. It'll be x minus mu over sigma. So in this case, it's just going to be x minus 174 divided by 20. Okay, so now let's do the math here. Okay, so to find the Z-score of 172, I'm plugging in 172 for x, okay, and then 172 minus 174 is going to give me a -2. So I'm doing 172 minus 174. Okay, I'm going to hit enter, and then I'm going to divide that by 20, and I'm getting about -0.1, or about -0.10. So Z-scores, we always round those to the hundreds, and the reason we do that is if you take a look again at your Z table, the Z values that are on there are rounded to the hundreds. Okay, so then the Z-score of 2. To find that, now I just need to put 192 in for x over here. Okay, so 192 minus 174. All right, that's giving me 18. Divide that by 20, and I'm getting 0.9 or 0.90. Okay, so here's what's happening. I'm going to draw 2 pictures, maybe help motivate this. So we know we're looking for this area along the distribution of X. Okay. And what the theory tells us, believe it or not, way over here at the origin, there's another graph called the standard normal distribution. Okay, and the area underneath both these curves is 1. And the area between these two z-scores, negative 0.10 and 0.90, that's the this little area here. And the theory tells us that those two areas are equivalent. Actually, yeah, so in another class, we proved that those two areas are equivalent. And so going back to the question here, the question is find the probability X is between 172 and 192. To do that with the Z table, this is going to be equal to the probability that Z is between negative 0.10 and 0.90. So the theory on linear transformations covered not in this class tells us these two areas are the same. And so this probability is equal to this probability. And then because your Z table only gives you cumulative areas, you actually have to take the probability that Z is less than 0.90 and subtract from that the probability that Z is less than negative 0.10. And if you want to draw a picture of that, might make a little bit more sense, the picture of these two areas, okay? So we're going to take, here's your standard normal curve, and 0.9 is about right here. And this cumulative, that's what this cumulative area is, the probability Z less than, that's this entire area. And we've overcounted, so we need to subtract off the cumulative area, or the area to the left of negative 0.10. So we got to subtract off this area. Okay, so now I'm going to go look these two values up in the Z table, find the corresponding areas, and subtract them. So let's see if I got a copy of that Z table. Here it is. Let's see here. I'm looking up for 0.90. And here it is, right over here on the positive side. And 0.90 would correspond to this number here, 0.8157. So this area is 0.8159 rather. And then I'm going to subtract from that this area here. So I'm looking up negative 0.10 in the negative z-score side. So let's see, there it is. Negative 0.10 gives me this probability, 0.4602. So now I'm going to subtract those two to get my answer. So it's a lot more work if you have to use the Z table to find a probability for a normally distributed random variable. So I want to encourage you to just use the calculator, just use technology if you need a probability. You don't necessarily have to use the Z table, but I just want to make you aware of what it is and how it was used. So before we had calculators and computers, statisticians had to use the Z table to find probabilities for a normally distributed random variable. And this is how they did it. They found the z-scores of their endpoints and then looked up the cumulative areas and subtracted them. Okay, if you take a look at the next question on the lab here, the probability X is less than 200, okay? Draw a picture for that. There it is. We know 174 is in the middle. So 200 is going to be right here, I guess. And it's a less than. They want us to find the probability x is less than 200. And so therefore, we're going to be shading to the left of 200. That's the area we need to find. And so we're just going to use normal CDF. With negative 10 to the 9 being our lower boundary and 200 being our upper boundary. Whoops, let's see here. Yeah, let's see, I need negative 10 to the 9. And the upper is 200 here. Alrighty. And we're getting about 0.90, about 90%, 0.9031, or about 90.3%. If you had to use the z-table to find this, which I recommend don't do that, okay? You're gonna find the z-score of 200. And the z-score of 200 will be given by x minus mu over sigma, which of course is 200 minus 174 divided by 20. So what is that? Okay, that's 26, and divide that by 20. So then we're getting 1.3. And so here's a picture of the standard normal distribution. So I've got two pictures, a picture of the normally distributed variable x and a picture of the standard normal distribution centered at the origin. 1.3 is going to be to the right of 0. And the area that's left of this, or the cumulative area associated with that, these two areas are equivalent. And so I'm just going to go over to the z-score table, or the z-table, and I'm looking for 1.3. Okay, 1.30 is right here. So bam, there's the answer. So that you can see that's nearly in line with what we got. We're only off by a 10,000. Actually, the table's what's off. The calculator gives you a more precise estimate. And then finally, this problem 3 over here. So I just wanted to illustrate how the z-table is used to find probability. They explain this in the book, but again, don't even worry about doing the problem this way. So last but not least here, question 3 here. Yeah, we're finding the probability x is greater than 55. Okay, so let's see here. We know the normal curve is centered at 174. So 155 is to the left of that. And look, they want us to find the probability x is greater than 155, greater than. So that means we're going to shade to the right. So then we're just going to use normal CDF now. And let's see, our lower boundary is 155. Upper boundary needs to be 10 to the 9th. All the rest of that is the same, and bam, we're done. The answer ought to be 0.8289. Okay, so now if you have to do this problem using the z-table, then you need to find the z-score of 155. Oops. And that's going to be 155 minus 174 divided by 20. So let's figure out what that is. Divide that by 20 now, and we're getting about negative 0.95. Okay, so this area underneath the normal distribution of x is also equal to, this is the standard normal distribution of z-scores, is also equal to the area to the right of negative 0.95, which is more like over here. Okay, so we're looking for this area. So when I go, and here's the thing, when I go to look up, when I go to try to find this area in the Z table, I'm not going to find it. Okay, if I look up this number, negative 0.95 in the Z table, I'm going to get, remember, the cumulative area, or the area to the left of that. Okay, so the way to do this is the probability that X is greater than 155 is equal to the probability that Z is greater than negative 0.95. So what we're going to have to do is we get the blue area off the Z table, right? We get the cumulative area off the Z table. And then we're going to subtract that from 1, the total area. So this is equal to 1, the total area, minus the probability that Z is less than negative 0.95. So we're going to take a 1 and we're subtracting off this blue area. And to get the blue area, we're over here on the Z. Where is that Z table? We've got a negative Z score. So we're looking for negative 0.95. So negative 0.9 is there. And then along the top row, 0.05. So the row column intersection is 0.1711. And so this is going to be 1 minus 0.1711. And of course, that should give us the same answer that we got before using normal CDF. And you can see, yeah, indeed it did. Indeed it did. Exactly the same answer. So that's the Z table. That's the standard and normal distribution. The book shows you how to find areas. The book shows you how to do problems like 1, 2, and 3 here using the Z table. And I would discourage you from doing the problems that way because it takes too long, and you can just use normal CDF. At the same time, if you've had this class before and you're comfortable with using the Z table, then I want to encourage you to bring that to the test and use that when you're doing the homework. So before I slide off of the standard normal distribution, I want to talk about, let's do a couple more problems with standard normal distribution. Let me see here. I can find those. Okay, so now I'm going to show you the inverse norm command on the calculator, what it's used for, and typical questions that might ask you to use it. So you've got a calculator command called inverse norm, and to access the inverse norm command, you just press second bars, and you can see that it's 3. Second bars 3. And for this calculator, you'll get this settings window for inverse norm. You need to know what the area to the left of the value of Z or X is that you're finding. And you also need to have values for mu and sigma. So this command, this inverse norm command, will give you a value of Z or X if you know what the area left of the value is, and also if you know what the values of mu and sigma are. Okay, so let's take a look here at a couple of questions. Let's go to, let's take a look here at question 3 and 4. Okay, so here's the question. Find the Z-score. Find the Z-score associated with the probability value of 0.8461. So when the book talks about probability value, they're talking about a cumulative area. So for this problem, the picture looks like this. It's a Z-axis, centered at 0. And let's see here. We're trying to find the Z-score that's somewhere over here. We don't know what it is, but we do know that the area to the left of that unknown value is the probability value, 0.8461. We also know that for the standard normal distribution, the values of mu are 0 and the value of sigma is 1. So that gives us the three pieces of information that we need to use the inverse norm command to find this unknown value of Z. So yeah, let's get that done over here. Remember, we're pressing second bars 3. Okay, and the area left is, let's see here, 0.8461. We know the values of mu and sigma are 0 and 1 for the standard normal, so that's all good. And now we're getting an answer. The answer is Z equals, we're going to round this to the hundreds, because we always round Z-scores to the hundreds, 1.02, 1.02. Yeah, that's the answer to number 3 here. Find the Z-score that has a probability of 0.8461. If you had to use the Z table to find that, well, we're going to make use of the fact that the positive Z table gives probabilities that are between 50% and 100%. To deduce that the given probability value is to the right of 0, or on the positive Z table. So we're just going to go and look in the table body for this number 0.8461, or try to find one that's close. There it is. Look, there it is. Okay, so now what Z-score is associated with that? And it's going to be, you see, 1.02. We just have to add this number and that number, and it gives us the 1.02. Okay, here's another question involving inverse norm. They want us to find the Z-score associated with the 90th percentile. So I'll use another sheet here. So if we had to draw a picture for that, it would be a picture again of the standard normal distribution, centered at the origin, right? Mu is 0 and sigma is 1. And let's see here, the number in the 90th percentile is going to be this value of Z, and to the left of this value of Z are going to be an infinite number of Z-scores. And what percentage of Z-scores will be left of that, left of this value? Well, 90%. So the picture looks like this. What value of Z is in the 90th percentile, or has below it 90% of Z-scores? And to get this, we're just going to call on inverse norm. And the area this time is 0.90. The mu and the sigma is 0 and 1. And we're going to get our answer. So second bars 3. And this time the area was 0.9. And we're getting about 1.28. Okay, so there are some other uses for inverse norm, because as I was saying earlier, the inverse norm command will give you a value of Z or X for a normally distributed random variable X. So let's take a look at some questions that are having us use that. There we go. Let's take a look at number 6 here. So in number 6, in a survey of women, United States, aged 20 to 29, the mean height was 64.2 inches. So mu is 64.2, and the standard deviation of heights was sigma equals 2.9. Assume that, so the problem says assume the heights are normally distributed. Okay, so then there's two questions. What height represents the 90th percentile? So here, X is the normally distributed random variable, or the normally distributed variable, representing women's heights. And they're asking us to find an unknown value of height or an unknown value of x. Yeah, so in the context of this problem, x is this variable here. We got a picture of the histogram or the distribution rather of x of heights, and we know that that's centered at 64.2. Okay, so now when we do part A, what height represents the 95th percentile? So we're trying to find this number x right here, and to the left of this height that we're trying to find is 95% of women's heights along this x-axis. So if the area left of this value is 0.95, then we're finding the value of x that's in the 95th percentile, about the height, which 90% of heights are less than. So that's another way to use inverse norm. To pull that up, let's see here, we're gonna have to calculator. So to answer this question, we're just gonna use inverse norm. Area to the left is 0.95, but this time the mu is 64.2 and the sigma is 2.9. So we're gonna have to change those values in the calculator away from 0 and 1. Second bars 3 gets me over there to the settings window. Area was 0.95. Let's see, mu 64.2. Sigma was 2.9. And so now I've got this height that's about 69 inches. If we want to round to the tenths, this is about 69.0 inches. So 5'9", right? 5'9" is the women's height in the 95th percentile. So in other words, 95% of women in this age group, their heights are less than 5'9". When you take a look at the second question, B over here, what height represents the first quartile? We have to remember that the first quartile is equal to the 25th percentile. Remember that Q1 is the number separating the lower 25% of heights the number that separates from the upper 75% of heights. And so therefore, Q1 is also equal to the 25th percentile. So if you're going to draw a picture here and locate in Q1 along the x-axis, well, it's going to be over here somewhere to the left of 2.9. Whoops, already gotten that wrong here. Let's see, 64.2 inches was the mean. Okay, and this value of x here is what we're trying to find. What height is in the 25th percentile, right? 25% of heights, women's heights in this age group, are numbers along the x-axis to the left of this value. They're less than that value. So we're going to use inverse norm here to get the value of x. Area is 25%, or 0.25. And the mu is the same, 64.2 and 2.9. So we're just going to change this to 0.25. And the rest of that stays the same there. And it's about 62.2 inches. So if you had to do the same problem, the way the book tells you to do it, okay, then here's how that would go. I wouldn't do the problem this way, but if you had to do the same problem, get 62.2 inches here, the way to do this is you use the z-score formula. And we know that that looks like this. When you solve this formula for x, you're going to get this formula here. X is equal to mu plus z times sigma. And we know what mu and sigma are. So mu was 64.2, and then plus some unknown value of z we're going to put in there, and then times 2.9. Okay, so this value of z right here, all right, that needs to be the z-score. That representing the 25th percentile. So to get this value of z, we gotta look in the z table for the 25th percentile, or 0.25. So I'm looking in the table body for 0.25. Let's see here. Here it is, right there. Nope, that's 2.5%, Jim. So I gotta be careful not to make that mistake, and I think the rest of us do as well. We're looking for 25%. And it looks like there's no exactly 25% there, but we found two numbers. Whoops, I'm sorry, I'm down here. We've got two numbers that are closest to 25%. And the z table tells you, let's see here, what was it? Do we have it right here? Oh, well, you just split the difference between this. Yeah, so to get this value of z, we're just gonna find the midpoint between these two values. Okay, so that's gonna give us 0.25. And 4, let's see here, plus 0.2483, and then we want to divide that by 2. So that's good. Oh, so you can see that is about 25%. But nevertheless, let's take a look. I'm trying to get a z value here. And what z-score is associated with this number here, you can tell that it is negative 0.67. And the z-score associated with this number, 0.2483, is negative 0.68. Okay, so the number I'm putting in here is going to be negative 0.6, either 7 or 8. No, let's just take the midpoint between that. So that would be 7.5. All right, so let's run that through and see if we got an answer that's similar to what we got using inverse norm. And you can see there we're getting the same answer as what we got before. 62.2 inches. So the long way to do it, I guess, is, you use this version of the z-score formula, and you've got to find the z-score representing the 25th percentile off the z-table. So that's how you would do it both ways.